Alright class, welcome to the bonus video for solving ice table types of problems. How do we work with the balance between initial conditions, equilibrium constants, and equilibrium conditions? Alright, so we're going to work through two bonus problems here. The first problem is laid out below. We have a reversible reaction, which is listed here. Chlorine is interacting with bromine reversibly to create two bromo monochloride. Wow, it's been a while since we've had to name compounds. BrCl. We have a sample that is 1 molar Cl2 is being mixed with a 1 molar sample of Br2. What are the equilibrium concentrations at 500 Kelvin, where our equilibrium constant is equal to 0.031? Okay, so this is going to be a pretty straightforward example problem where we're going to lay out our ICE or ice table. We can fill in the gaps already with what we know just from the wording of the problem. So we are told that we have a 1 molar sample of chlorine and a 1 molar sample of bromine, meaning that we can put in a 1 molar sample here under the chlorine, a 1 molar sample here under the bromine. Now we are told that the reaction begins when Cl2 and Br2 are being mixed together. There is no mention of BrCl being present initially, so it's safe to assume that we have nothing, no BrCl to start with. Okay, so if we want to predict a change then, which direction is the reaction going to spontaneously move? Well, the first thing that we can notice is that we have 0 molar product initially. Now this means that the reaction is going to have to shift in the direction to actually create product, right? We physically can't go backwards. We cannot create reactants from literally nothing. So we're going to have to go from reactant to product here, meaning that our change is going to be minus x for each of the chlorine and bromines, just minus 1x since we have stoichiometric coefficients of 1 in front of them. And on the product side, because we have a stoichiometric coefficient of 2, we're going to be adding 2 pieces of change, 2 units of change, 2 x's for every 1 shift away from the reactants. So yes, we're not doing total stoichiometry here, but the stoichiometric balance is still going to matter somewhat. So what this means is that we're going to have, at equilibrium, a 1.0 minus x concentration for Cl2, a 1.0 minus x concentration for Br2, and a 2x concentration for BrCl. All right, so now that we have some equilibrium information, we also have an equilibrium constant here. We can write out an equation much in the same vein as what we did in the example problems from lecture. So we have a Kc here, or equilibrium constant, which is going to be equal to the concentration of BrCl squared. Again, we have a coefficient of 2, meaning we have to square the concentration of the BrCl. And we are going to, in the denominator, have our reactants multiplied together, the concentration of Cl2 times the concentration of Br2. Now we have some equilibrium values that we can actually insert into the equation from our ice table here, whatever our partial changes are going to be. So we have a 2x squared in the numerator, right? 2x coming from the table. We still have to square it since the square is in the equation, so we have a 2x squared. In the denominator, we have a 1 minus x, and yes, this is 1.0 if we want to keep sig figs, but I also want to save on some space, so I'm going to shorthand this with just a 1 minus x. Okay, so from here, since we do have a value for what Kc is equal to, right, we know that Kc is equal to 0.031, we can insert that number here on the left-hand side, and we can go about solving the problem using a quadratic equation, etc., etc. However, in the main lecture, I'd also mentioned that if you spot any type of algebraic shortcuts, absolutely use them. Use any type of shortcut that you can find. And here, before moving forwards, if we kind of take a moment to inspect the equation as we have it laid out, we can actually see that there is an algebraic shortcut here that's going to save us a lot of time. Now our equilibrium constant, again, is 0.031. And the equation as it is on the right-hand side, well, there's not really a way to shorthand what the numerator is. This is still 2x squared. The denominator, though, notice that we're taking the same thing, 1 minus x, and multiplying it by itself, right? 1 minus x. This is the same thing as 1 minus x squared. And if it isn't immediately obvious how that has helped us, let me show you. We now have a squared in the numerator and a squared in the denominator. This is the same thing as if we were to pull that squared out of the entire fraction. And here now we can see that we have one big thing squared. And in order to remove a square, algebraically speaking, like, yes, we can distribute the square as we could have done, go through the quadratic equation, but the easiest way to get rid of a square is just to take the square root of both sides. And now we have completely removed the square from the problem. The square root of 0.031 is equal to 2x divided by 1 minus x. And now we have a very simple way to algebraically rearrange and solve for x. And in fact, if we do so, we find that our x is equal to 0.0809. Right, so this algebraic shortcut saved on a lot of time. We don't have to go through, rearrange a quadratic equation. We don't have to use the quadratic formula. It is just a straightforward rearrange and solve for x. Push x to the left-hand side of the equation, push all the numbers to the right, and we end up finding that x is equal to 0.0809. Now, this value can be used then back in the equilibrium row of our equilibrium table. If we take 1 minus x, we're taking 1 minus that 0.0809. And what this gives us is an equilibrium concentration of our chlorine that is equal to 0.919 molar, as well as our bromine being equal to a 0.919 molar. Just to box these off so it's a little bit easier. And for our product, we're going to take 2 times what our x is, which is going to be equal to a 0.1619 molar. There. So now we have our equilibrium concentrations both for reactant and product in a fraction of the time. So the setup of the problem, we do the exact same way, moving these unknown x's, these unknown changes into our overall equilibrium expression, which we wrote here. Up until this point is basically the same. It's at this step where we realize, oh, hey, there's a shortcut here. And so this is going to be one common type of shortcut that you can look out for. If you can cancel out your squareds using a square root, that's going to save you a lot of time. Now, if you go back to the previous examples that we worked through in lecture, we actually could not utilize this shortcut at any point. Those problems were designed to be problems that we have to lay out or use a different type of shortcut like the second problem we worked through where k was super, super small. This is a problem where k is not super, super small. Our k, we can see, is not 1,000 times smaller than our initial conditions. In fact, it's only about 100 times smaller. So our k is not so insignificant that we can just drop change in x, but instead we found a different shortcut algebraically speaking, which is also totally mathematically valid. All right, so if you have any questions on the math as I worked through here, definitely let me know. If you want to take the time to kind of work through this math the long way just to show yourself that yes, your x is going to still be equal to 0.0809. Also, get that practice. Again, practice, practice, practice. Whatever you need to really get this type of problem under your belt comfortably. Okay, so our second example problem is a little bit different, but it is a way to use ice tables to solve this type of reversible reaction problem. So let's work through this slightly more detailed problem. We can see a new way to use these ice tables in a very effective kind of preparatory means. So, all right, second bonus problem. How many moles of our chlorine must be added to 1 mole of our antimony trichloride in a 2-liter container to reduce the amount of antimony trichloride down to 0.7 moles. All right, so here we're not necessarily looking for equilibrium conditions. We are looking for an unknown initial condition. How many moles of chlorine must be added? This is phrasing that lets us know that we are looking for something pertaining to the initial conditions. So let's see how the setup of the problem is going to end up being the same, but then we're going to follow through with it in a different way. All right, this is a reversible reaction. We can see a forward-backward reaction arrow here. We have a Kc that is given to us, which tells us that we're still going to be setting up some type of ICE or ICE table. So any value that goes into an ICE table, since it corresponds to the equilibrium constant, where your equilibrium constant, the values that we're putting in here are antimony pentachloride concentration, all divided by antimony trichloride concentration times chlorine concentration. The word that I've used now multiple times is concentration. The units of concentration are what matter in this Kc. This Kc with a subscript of C, meaning that this value right here pertains to when our values for our reactants and products are all in units of concentration. So what is going to be very helpful for us is to lay out the ICE table with all of the information we have in units of concentration. So our antimony trichloride, we are told that we have 1 mole of it to start with, and it is in a 2-liter container. So the concentration of our antimony trichloride initially is going to be 1 mole divided by 2 liters, or 0.5 molar. This is the value now that we are going to enter into our ICE table down below. All right, so we have a 0.5 molar concentration for the antimony trichloride. Our chlorine, we don't know. We don't know how many moles are being added here. We do know the volume of the vessel, but its actual concentration is 0 moles divided by 2 liters. Like, we know the 2 liters bit, but we don't know the number of moles. So this is the first unknown that we're going to lay into this table. Now, the antimony pentachloride concentration is also not told to us, but in laying out, kind of reading into the terminology of this word problem, we are told that chlorine is being added to antimony trichloride. Antimony pentachloride is not mentioned anywhere, so for much the same reason we did in the previous example, we're going to assume that there was nothing to start with. No antimony pentachloride. All right, so what this does for us is that it tells us that our reaction, again, is going to be shifting from reactants to products. We're going to be creating some amount of product in this reversible reaction. And because the stoichiometric coefficients in front of everything are 1 here, we're going to be losing x's on the reactant side and gaining an x on the product side. Okay, so this is going to look strange, but bear with me for a second. The 0.5 minus x will be our concentration for the first reactant, our SbCl3. The chlorine is going to be our question mark minus x, whatever this concentration is equal to. Concentration divided by 2 liters, let's just keep it super consistent here. Question mark number of moles divided by 2 liters is our minus x is going to be our equilibrium concentration. All right, and our product, the SbCl5, will have a concentration that's just equal to x. All right, so if we were to set up an equilibrium, like Kc kind of problem, equilibrium constant expression, what we can see here is that we have our unknown x, but we have another unknown, this question mark here. And if we have 1 equation and 2 unknowns, technically we can't solve it. So what this tells us is that either we have a problem, and this bonus problem, as I have laid out here, is unsolvable, or there's another way to solve it. So let's go to the wording of the problem and see if there's any information that we have not used. So we've used the 1 moles of our SbCl3. We've used the 2-liter container. We have not used this 0.7 moles anywhere. So let's see where this comes into play in the wording of the problem. We are looking for how much Cl2 must be added in order to reduce the amount of SbCl3 here at equilibrium. This is kind of reading between the lines a little bit, but we want to reduce the amount. And so it would make sense that this amount would be reduced when we have gotten to equilibrium. So we're looking for the equilibrium value in moles of our SbCl3 to be 0.7 moles. In other words, we are looking for this value right down here to be equal to 0.70 moles divided by 2 liters. Again, we want everything to be in units of concentration. So what we have now found is a way to solve for x without needing to use this entire expression here. We have found a way to solve for x by setting up our initial conditions change, and now we are told what the equilibrium conditions for one of our pieces is going to be. All right, so our x, 0.5 minus x, is equal to, if we solve for this concentration, 0.35 molar. So now we have a means to figure out what our x is equal to. If we subtract this 0.35 to the left-hand side, move the x over, we find that x is equal to 0.15 molar. And we can plug that in everywhere, right? X is x no matter where it is. So the change that is happening is a minus 0.15x minus 0.15 plus 0.15 all across the board. And so the equilibrium concentration for the SbCl3 here is going to be equal to the 0.35 molar. The unknown concentration for the chlorine, yes, we still don't know what this question mark is right here, but we do know that we are going to be losing 0.15 molar, and the equilibrium concentration of our SbCl5 is also going to be 0.15 molar. So now we have an equation that we can turn our eyes back to that has, this one equation and only one unknown. And this one unknown this time is going to be the concentration or the molar value for the chlorine at equilibrium. We're not necessarily solving for x since we just solved for x. We're looking for something else now. So if we set up our equilibrium expression, let's set up these lines here. We have a 5.65 that is equal to 0.15 molar. Again, our equilibrium concentration for the SbCl5 we just found. This is going to be divided by a 0.35 molar, which is from the antimony trichloride, the value right down here. And this is going to be multiplied by whatever this term is. Our question mark divided by 2, all subtracting out 0.15. That looks kind of schmooshed there. If we algebraically, though, rearrange and solve for what our question mark is equal to, right, since we've now set up an equation that we have the means to solve for what our question mark is, algebraically speaking, I will leave the steps to you to double check your ability to solve this type of problem, but our question mark, our number of moles, right, since that's what our question mark is number of moles divided by liters. Liters are going to go away. We will have a value that is equal to 0.452 moles. So this is how many moles of chlorine must be added initially in order to get this reaction to move a predetermined amount. If we think of this more conceptually, it's like we have a reversible reaction we know we're going to be working with, and you're shooting to get a certain amount of reactant left over. You want to still have 0.7 moles of your antimony trichloride. And the way that you're going to do that, you're going to push this reaction forward only a slight amount by adding 0.452 moles of our chlorine in this 2-liter vessel to get the predetermined amount of product that you want. All right, so here are then two example problems, bonus problems that hopefully kind of seeing more of this math, how we can think about using these ice tables has been helpful to you. There are definitely more problems that we are going to be working through. Basically, for the rest of the semester, we are going to be doing these types of reversible reaction problems. So we're going to be getting plenty of practice, but the more practice you get sooner, the easier it will be as we progress into the more difficult concepts. So yeah, again, let me know if you have any questions, but otherwise, thanks for watching.